Okay, if you're viewing this video, you should have already seen the video lesson on preparing a standard solution from a solid. I'm just going to show a video clip, which I had intended to show previously, but now will be a good review, which overviews this process from calculation to final mixing. Let's have a look.
To prepare a solution of known concentration, we must first weigh the solute. We need an accurate volumetric flask designed to hold 250 milliliters. We first add the solute to the empty flask. The flask is filled about halfway with water and mixed to dissolve the solute. We add water in stages. Combining all the solvent with the undissolved solute in one step can lead to inaccurate measurements. We mix again. The solution is prepared.
Okay, now I want to return to this summary sheet here on the steps to prepare a standard solution. You'll have noticed that in that video clip you saw there were only probably about 3 steps or 4 at the most. It was the calculation obviously wasn't discussed. The mass measurement was shown. The dissolving step was skipped. The transferring was done directly from the filter paper or what looked like a piece of paper. It could have couldn't have been a weighing boat of much size, and then the bringing to volume and mixing were done at the end. So I want to just think about that and maybe the advantages and disadvantages of that approach. If we were to look at the sources of error, possible sources of error or complications in your solution preparation, we're certainly going to have, we can't cite calculation as a source of error. You should always be checking your calculations. So that's step 1 involves no error. We will assume that we've checked all the values. Mass measurement, there could be a source of error with the use of the balance. What I would say, probably your largest sources of error would be use of balance as a minor source of error, but probably the transfer, solute transfer from the weighing boat. That one would involve a little bit of potential loss of your chemical. The next likely source of error is going to occur in probably step 4 when we're transferring the partially or fully dissolved solute. So we could have incomplete transfer or incomplete rinsing. Could call that kind of 2 separate possible sources of error. Would be incomplete transfer slash which would be a result of insufficient rinse step or rinsing. We could have spillage occurring at any of these steps. So spillage of solution. Probably the only other source of error at the end, going back to step 5, would be bringing to volume. The mixing, I can't see anything occurring there out of the ordinary, but the bringing to the volume, again, if we were to slightly exceed this this fill line, that would definitely produce a concentration a little bit lower than what we intended, because we've put more solvent in than we had calculated. So overfilling the flask. Okay, so there are some things we have to watch for. In addition to errors involved in preparing a solution, we could have factors that would limit the type or concentration of solution that could be prepared. Using that method, we have to be able to work with a volumetric flask. 250 milliliter volume was mentioned there in the video. That's a fairly common volume for volumetric flasks. A 1 liter or 2 liter volumetric flask, though they're available, you could purchase them. It's a little bulky to be working with. It's fairly large, and we don't often want to make that much solution. It could lead to a lot of waste. I would say that the type of solution we want to consider here needs to be fairly soluble. So we need a highly soluble compound, which pretty much limits us to mostly ionic compounds or some acids, molecular acids, but mostly ionic in nature. The concentration, again, is going to be dependent upon the solubility. When we look at the solubility of a given compound, that's how many grams of solute will dissolve in 100 milliliters of solvent. We'll look at solubility a little bit more in chapter 7. There's going to be a limit there as well. We could have a highly soluble compound, but we may not be able to just dissolve without limit an amount of solute. So those two factors probably are going to determine the type of solution. Ionic compounds are the most obvious ones to use for making standard solutions, and the higher, more highly soluble compounds you'd be able to prepare a more concentrated solution. As the solubility is low, then we would have dilute solutions possible, but for high solubility, we could make more concentrated. Now, if we turn our attention to dilution, just as we looked at preparing a standard solution, when we want to dilute something, we're wanting to, for the same amount of solute, add more solvent. And so the easiest way to do that would just be to take an existing standard solution and prepare a precise addition of solvent. So in this case, a dilution is defined as the process of decreasing the concentration of a solution. So we don't need a specific definition there. The only definition that comes into play here is the term stock solution. So on page 302, the definitions you may want to just take note of are in the margin dilution, which is decreasing concentration, just to use a quick shorthand there. Stock solution is the other one. Stock solution is what we begin with, and usually the stock solution is one that's already available on the shelf. So it's quite often concentrated. And you would maybe relate to this a little bit in the home setting. You have concentrated cleaning solutions which need to be diluted. The concentrated bottle will be your stock solution. So it's readily available, and quite often it's highly concentrated. So when we prepare a standard, our standard is precisely measured and precisely prepared. It can become the stock solution for dilution. All right, so the steps to prepare a standard solution by dilution. Let's have a look at the visual here. The steps involve, from a volumetric flask, which is our stock, again, a concentration calculation needs to be made. Let's look at the formula a little bit here. When we prepare dilution, the amount that we're taking out from the stock solution ends up being topped up with more water, but the number of moles that we removed from the stock solution is the same in that pipette as what we have in the final flask. So what we say here is that the initial number of moles removed and the number of moles final in the flask are equal, okay, as long as we don't spill anything. How do we calculate moles? Well, moles from the molar concentration formula is a product of what the concentration is and how much we have as a volume. So the initial conditions are I and final conditions are F. So we can say that the initial volume removed multiplied by the initial concentration represents the initial number of moles, and that would be equal to, assuming no spillage occurs, the final number of moles, which would be based on the new concentration, which would be the diluted concentration CF, and the final volume, which would depend on the glassware that's used. So we're taking a small volume, bring it up to a larger volume, but what happens is we actually start with a more concentrated solution and drop down to a less concentrated solution. So dilution involves an increase of solution volume, but a decrease in solution concentration. Let's just pause here and have a look at the remainder of the steps. This formula here, which is VICI equals VFCF, is called the dilution equation. Sometimes it's seen maybe in textbooks as V1C1 equals V2C2. However, I would say maybe better to stick with I and F because V1, V2 might get you thinking about gas laws, and it'd be better to avoid any confusion there. So VI-CI equals VF-CF. That's going to be our first step, which is the calculation. So as you're going through this slide here, you're filling in some information. You're also updating the steps involved in preparing a standard solution by dilution. So that'd be step 1, which is the calculation. Step 2 is going to be, as shown there, about half the final volume of water is immediately put into the new volumetric flask. And then we take a pipette bulb, and of course what's not shown here is the person is holding onto the pipette bulb. It's not a turkey baster, so we don't jam it on the end of the pipette. It's just gently touched to the top of the pipette, and the water rinse is done. That just cleans out the pipette in case there were any residues from previous usage. Should have been well cleaned, but we rinse it out with water. Then we will rinse it several times with the sample to ensure that it's well coated throughout the pipette with the initial solution. Then we're going to transfer the amount that we need, and that's part of the calculation. We're going to take here the initial volume needs to be calculated. That would be assuming we know the final volume, which is your 100 milliliter volumetric flask. The final concentration, you decide what you're going to do. If you take 0.5 moles per liter and you dilute it down to 0.05, that would be called a 10 times dilution, meaning that you're taking 1 part of initial solution and you're diluting it to up to 10 parts of final solution. So you need to know your values for the initial final concentration, know your final volume, and your initial volume would be calculated there at 10 milliliters. So here we would have a 10 milliliter volumetric pipette, which is going to now be used to remove from our sample beaker. Make sure you put lots of solution in this beaker so that you don't accidentally draw up air into the pipette, so you have enough of your sample there to rinse and to transfer. Then that is carefully transferred into the pipette. I would say a flask is not going to be needed at this point. We could ensure that the pipette is put into the neck of the flask, and then at this point, when you deliver all of this 10 milliliter, we'll say, into the flask, you would want to make sure that all of it is removed. And sometimes what's done is you would cap it at the top with your hand and place your other hand over the middle of the bulb here, just to cause the air inside to expand, and that would force out any little bit of liquid that might have been in the bottom there, which is part of your 10 milliliters. Once that's been done, you're not going to rinse your pipette. If it's got grease inside of it, it might trap some droplets of the solution, and that's why we want to make sure they're well cleaned, but it should be well dry after we've transferred it all. Now we're going to top up with water using a wash bottle here, and then as we get close to the top, the dropper is used. I rarely use a meniscus finder or anything like that, but it could be used if you're if you had vision problems, or if you wanted to really be very, very meticulous about your precision. So once that's done, then you're going to, as before, mix, inverting in between, and just carefully releasing any built-up pressure. So steps 4, 5, and 6 are the transfer, topping up, and the mixing. So you can update your list here. Again, activity 2 we'll just defer for now until we get into some class work with preparing standard solution, and in this case by dilution. We would follow up by deciding what we want to dilute to. All right, now having seen that, let's just view a short little video clip and see how that compares with their example.
To prepare our solution using the dilution method, we first obtain 2 milliliters of stock solution with a pipette. Filling the pipette with stock solution to the mark on the pipette ensures that we have 2 milliliters of this solution. We add the 2 milliliters of more concentrated solution to the 500 milliliter volumetric flask, touching the side of the flask with the pipette. We add water to the mark on the flask. After mixing thoroughly, we have exactly 500 milliliters of a solution.
Okay, so how did that compare to the steps outlined here? Well, again, the calculation was in the background. We saw at the very end there was a concentration listed, which I cut off, but the amount of the solution was decided at 500 milliliters, and then you'll notice that immediately the video cut to transferring from the pipette, so there was no rinsing the initial flask. I think in that case it wasn't mentioned about half filling it with water. That's not extremely important, but just providing some solvent for the concentrated solution to begin to mix with is a good strategy. So I would tend to follow this, especially step 3, because unless you're starting with brand new volumetric pipettes, you're going to have the need to at least rinse them to ensure that you're pretty much transferring as much as possible just your solution. There could be dust inside that could contaminate, so getting that rinsed off with water and at least the solution a couple times is good practice. When you look at the outline of the steps involved there at the very end, again, we come back to as we saw before, sources of error or complications. We have transferring occurring, we have potential for spillage, we have potential for overfilling. So all of the sources of error that you mentioned on your previous summary here at the bottom, you should also repeat those just to reinforce that. As far as limiting factors, the final concentration obviously can't be even equal to the concentration of the initial solution. So the limit to the concentration there of the solution using that method would be the extent of the dilution. So depending on how much solvent we're adding to the amount of initial solution would obviously affect that. So we can really bring it down to the final volume is going to be determining really the extent of dilution compared to the initial. And of course those two values alone really determine the ratio of the concentrations. All right, now here we have again, coming back to the solution preparation. This one here, maybe at this point you've had a chance to complete and check your answers with this practice worksheet on the website. So now I'm just directing you to dilution. In this case, most of these questions are going to just have you working through the dilution equation, and you're not working with masses for dilution because you have a liquid stock. So here, when it directs you at the beginning to concentrated reagents, that would be the most common commercial reagent, and you want to refer to the back of the book under the appendix called concentrated reagents, which you'll find in one of the appendices. So right after the elements, you have common chemicals, and appendix C5 on page 636. I'll just jot that down here for you. Appendix C5, page 636 is where you'll find list of concentrated reagents, and it includes acids and bases on that page. So when you're looking at these questions here, you're usually just needing to identify which volume is provided here. Most of the time it'll be your final volume. You've already decided that, and what you really want to know is how much volume should you remove from the stock. So here you're going to be diluting 150 milliliters, so that would be identifying as the initial volume removed. It's a concentrated commercial reagent, which is ammonia. So you want to look up ammonia and identify ammonia as a base with a concentrated value at 14.8 moles per liter. So concentrated ammonia is going to be 14.8 moles per liter. That would be the initial concentration, and that's your stock solution. So now what you're trying to determine is for a final volume of 1,000 milliliters, then that's your VF, and you've got a liter of solution to obtain what would be the final concentration. So here you can approach this a couple ways. You can either say, well, I know how to calculate concentration. Concentration is number of moles divided by volume. And I know how to determine number of moles. It's concentration times volume. So I can start with the initial conditions are I have an initial volume and an initial concentration. From that, I can say, well, the initial number of moles is equal to the initial concentration times the initial volume. Make sure, of course, that this is in liters, so that's 0.150 liters. So if we multiply those two values together, then we'll get how many moles were removed. And that number of moles gets put into that final 1,000 milliliter volumetric flask, and so that number of moles is equal to the final. And so concentration final is just going to be equal to the number of moles final divided by the volume final. The volume final is 1,000, and the number of moles final is the number of moles initial because it hasn't changed. You just transfer that over. You just remember the visual. You're just taking that whatever 10 milliliter amount from here, and now it's going into here. So the rest of it's just solvent. So you have no increase or decrease in the number of moles that have been transferred. So going back to this, the calculation of final concentration can be done in steps. Of course, you can omit the middle step, which is identifying moles, and you can just use CIVI equals CF VF, and then solving for final concentration would be concentration initial divided by volume final. Of course, within that, can't help but see that you're taking a product of concentration and volume, which of course is your moles. So it doesn't matter how you calculate the final diluted concentration, and you can use the dilution equation, which has been introduced, or you can just do it in steps and just use the equations which have already been established, which depended on concentration, moles, and volume. The rest of these questions are just going to be similar, except you may find in some of them you have different types of concentration units. So in 3, it is a percent solution. In number 2, it's a parts per million. You never know what it is you're going to be trying to solve for. Okay, so those one will complete in class. And again, at this point, I don't think there's a need to assign any additional questions out of the textbook for practice. You've got the solutions which you can check on the website, and you've filled in your note. So next steps would be looking at putting this into practice, preparing standard solutions, making dilutions, and then doing some chemistry with those. Okay, take care.